Hi everyone, I'm Kat Massey, the Director of the Ambient Air Division at Apex Instruments. Some of you might be familiar with Apex Instruments for our stack testing equipment, or possibly for our Custom Mobile Laboratories division. Last year, we launched our Ambient Air Division, where we represent two different product lines, a multi-pollutant sensor system and a Microscale Gas Chromatograph, which is used in in-field speciation of volatile organic compounds. Today, I'll be discussing this technology, the VOC analyzer, and I'll be sharing results from a laboratory evaluation of a MEMS-based microscale gas chromatograph for VOC analysis. The motivation behind developing this instrument stems from the need for real-time quantification of volatile organic compounds in the field setting. Given that our VOC analyzer is a relatively new technology, the goal of this work was to evaluate the performance of the analyzer using a third-party laboratory. In this case, we're using AECOM's laboratory in Austin, Texas. I'll share the methods that were used to test the analyzer, and then I'll share a selection of the results from this testing, including some various benzene sample tests, mixtures of VOCs, various humidities, and a brief look at historical data. Finally, I'll summarize the work here and highlight some future tests and collaborations that we're seeking. To give some context to why this VOC analyzer was developed, it stems from the need for in-field speciation of VOCs and quantification. So some folks might be familiar with EPA method 325, which describes the collection and testing of volatile organic compounds at or near facilities that have VOCs present from either fugitive or area emission sources. And it details how these VOCs are collected in the field using passive sampler tubes that have been deployed in place for about 14 days. And then these passive sampler tubes are collected, sent to a laboratory for analysis, typically via thermal desorption, gas chromatography, and mass spectrometry. And then results are communicated back to the end user. And this cycle typically takes around 21 days. In this time, you don't have much resolution on what has occurred. You don't really know exactly when VOC emissions might have occurred because it's a cumulative summary of total emissions during this time span. Additionally, this can be a pretty expensive process, although it is required by EPA. These recurring costs are quite extensive, and it gives you a limited opportunity to really respond to a VOC emission event. The solution that our collaborators developed involves sending a portable gas chromatograph into the field and continuously monitoring for VOCs. Pictured here is our micro gas chromatograph that is being powered here by solar panels and has a battery backup system. We're able to measure and speciate many common VOCs with this device with a limit of detection in the low parts per billion range. You're able to get results in just a few minutes, operate fully off-grid with the use of a solar panel, and conveniently, you do not need any carrier gas. We use just ambient air here. We are not using PIDs or photoionization detectors, so we don't experience the same level of sensitivity drift as other systems, so you don't need to calibrate the device very frequently. It's a pretty low cost system and it weighs only about 16 pounds, and we have an optional C1D2 enclosure as well as a bump test kit. To give you an example of how the device works, we have pictured here on the bottom side is where the sample inlet is. This supports where the ambient air passes into the system. Then the analyte passes across the MEMS-based chip. We have a bidirectional pump that pulls the analyte across the sample. The analyte pre-concentrates at this pre-concentration material for a set sampling time. And then we flip the direction of the pump. We heat the pre-concentration material. The VOCs desorb from the pre-concentration material. They become separated by the meter-long column as part of this microgas chromatograph, and they're detected by passing over the dual capacitive detectors. This slide gives you an example of the type of chromatogram that's generated from this device. If folks are familiar with gas chromatography, you'll quickly realize that this chromatogram looks a little different. There are two sets of signal data here, one for each of the two capacitive detectors. One of the detectors is sensitive to polar and nonpolar compounds, while the other detector is just sensitive to polar compounds. By using these dual capacitive detectors, we have three different means of quantification for VOCs. We have the standard quantification our identification of chemical species due to retention time, and we're able to determine concentration from peak height. But we also have a third parameter, which is the peak height ratio, or the distance between the peaks. And based on using that parameter, we're able to identify chemical species based on polarity, and this gives us a third parameter for identifying VOCs that have similar elution times. Now switching gears into the bulk of the presentation, which is the testing parameters performed by AECOM. I'll discuss how the Omni 2240 Micro GC was challenged to different concentrations, compounds, and humidity levels. And AECOM found that the device performs very well, even under 100% humidity conditions. I wanted to just also share this disclaimer from AECOM that the test results presented here are intended solely for the purpose of sharing information and do not represent or constitute endorsement, certification, or approval of any products or services by AECOM. Results are provided as is and reflect only the specific conditions under which the testing was performed. So the laboratory testing occurred in AECOM's Austin, Texas facility, where they configured the gas chromatograph, attached it to a gas delivery system to control the gas flow and humidity of different VOCs. And they referred to us for clarity on how to set this up. The particulate matter on the front end of the sample inlet was initially removed, and the black polymer tubing that you can see pictured in this image was connected from the inlet was loosely positioned inside of the swage lock fitting that was connected to the gas delivery system. I wanted to share a couple setup and interpretation notes before we move on. So sampling times here for the Omni 2240 Micro GC can easily be managed from the cloud-based platform where you control the performance of the testing of the device and data analysis. Please assume that humidity was around 40% unless otherwise stated. The use of ND throughout the slide deck, it refers to not detected. External filters were typically removed for all sampling unless indicated otherwise. And you'll see throughout these the data results slides that the use of a red dashed line indicates a plus or minus 30% of the theoretical value threshold. And this is a parameter that AECOM specified, and it typically is what they use to determine typical control limits, especially when working with field instrumentation. So this is just a helpful visual to use throughout the slides. This quickly summarizes the different tests that were completed. So we're looking at different benzene concentrations. We're also going to be looking at different test standard mixtures, changes in humidity, and then the carryover from different high concentration tests. And please note that in general, the VOC analyzer's limit of detection and maximum measurable concentration are both inversely proportional to the sampling time specified by the user. So moving on to the benzene tests. All right, here we're looking at the VOC's performance for measuring 5 parts per billion of benzene with a 15-minute sample time. You can see the results are compiled in the table and then showed on the graph to the right. And here there were 13 tests performed, all looking at 5 parts per billion of benzene. We see the most variation in the first run of the day, and you can see from the table that there were occasional trace measurements for toluene or xylene, but these values were either right at or below the limit of detection. In general, the performance for the device at this 5 parts per billion threshold was within the theoretical value range that AECOM specified. For the 25 parts per billion benzene sampling, the sampling time was set to 5 minutes. Here, 7 tests were completed, and we observe a trend towards slightly underreporting of benzene. This is likely due to the short sampling time, as typically with this unit, we recommend running at least 10-minute sampling times or longer. However, we do offer a different model, a different unit altogether, that has a more accurate short measuring sampling time. Again, in this data set, we see the largest variations in measurement occurring with the first run of the day and occasional xylene readings, but these values are below the limit of detection. This slide details various benzene concentrations with various benzene concentration inputs with a 5-minute sampling time. We see slight trend towards underreporting again for the lower concentrations and a slight trend towards overreporting for the 250 parts per billion sample. The blank run immediately after measured 7 parts per billion, but this is below the limit of detection. Here we are observing 25 parts per billion benzene at various sample times. Keep in mind that the limit of detection varies with sampling time. In general, the VOC analyzer underreported benzene slightly, but was within the plus or minus 30% threshold range as established by AECOM. Moving on, the next few slides will show tests that summarized the evaluation of VOC mixtures at various humidities. The tests evaluated here show 25 parts per billion diluted from the test standard mixture listed at the top. The chromatography library for benzene, toluene, M and O xylene was used. And please know that other compounds from this mixture are detectable by the VOC analyzer, but at this time the libraries for those compounds have not been built out yet. We see that our VOC analyzer is able to perform quite well and very accurately speciate benzene, toluene, O-xylene from the complex mixture. The standard mixture listed M and P xylene as a combined item, indicating that the diluted mixture contained approximately 12.5 parts per billion of M and P xylene. This explains why the M xylene measurement appears to be on the lower end of the plus or minus 30% range. But this is again because the combined total of M and P xylene was about half as much as the other compounds that were closer to 25 parts per billion. So really, the analyzer performed quite well, being able to speciate and pretty effectively quantify the difference in P and M xylene. The next test here measured 25 parts per billion of a PAMS audit can at 70% humidity with a 15-minute sampling time. Here we're seeing strong results were obtained for the benzene, toluene, O, and M xylene, where O xylene was nearly at the values measuring within plus or minus 30% of the theoretical range. These results at the increased humidity support that the VOC analyzer is capable of speciating VOCs even from a complex mixture in a very humid environment. This next test shows, again, the test audit can with the compound listed to the right. And each compound here was nominally about 5 parts per billion, and the sampling time was set to 15 minutes with varying humidities. This summary shows that for all of the tests completed using this test audit can and 15-minute sampling times, the VOC analyzer was capable of accurately measuring the indicated concentration of gas. Please know that pentane and hexane are also detectable by this VOC analyzer, but again, the libraries have not been built out yet. The final results I'll share here have to do with the historical effect of sampling. So the data here compiles 15 runs, and this is all for 5-minute sampling times. And the test results here are all for blanks. So this is just nitrogen and room air. No VOCs are flowing. And we're looking to see historical effects if any VOCs are present. In general, we're seeing very trace or hardly any VOCs present with the blank samples that were run thereafter. And please note that for this 5-minute sampling time, the limit of detection is below 10 parts per billion. So really, all of the signal that's being seen here is noise. Similarly, this is another combination of historical data. Instead, this is for 15-minute sampling times, again, of blanks, so comprised of nitrogen and room air. And here we're also just seeing very trace levels of VOCs present occasionally after a particular run. Note that the limit of detection here for the 15-minute sampling time is around 2.4 parts per billion. So again, most of the signal here is below the limit of detection. Finally, just wanted to quickly summarize the results from all of these studies. So we exposed the VOC analyzer to different benzene concentrations, to various mixtures, and to various humidity levels. In general, we saw very accurate results for benzene and toluene measurements. The instrument performed well under all different humidity conditions. We did see that the first run of the day was typically a little less accurate, and we observed a slight trend towards underreporting values, but the accuracy tended to improve with increased sampling time. For both benzene and toluene, nearly all the measurements were within the plus or minus 30% of the theoretical value threshold. M-xylene, we are able to distinguish from p-xylene, which is quite difficult to do. And then we saw a slight trend towards underreporting M-xylene and a very slight trend towards overreporting O-xylene. For future work, we are continuing to look for different collaborations. So if you have a laboratory or a field site where you'd like to test the instrument, we do occasional demos. So we're seeking partners for field testing. We're also looking to do further laboratory testing of the equipment and looking for other opportunities to further test the environmental conditions of the instrument. With that, I'd like to thank you for listening and encourage you to ask some questions either now or offline.